right, welcome back. We are Game 2005 in the fall 2020 semester at George Brown. It's Game Physics and we're week 12. And we got a couple things to talk about that are different today than I thought I would be talking about with you, but hey, let's do it. So let's get into our schedule for today. So we're sitting at week 12, and this week we're starting to talk about 3D collisions, and next week 3D response and so on. And when I was looking through the assignment 4, I was going to get you guys to do things with an SDL engine or some kind of OpenGL framework. And as I was looking through it, and I was looking through your submissions for what you've given me already, I suddenly became quite worried. And I'm not saying because your submissions weren't good, but because of the framework that I'm going to give you, or that I was supposed to give you, was something that we really haven't talked about until now. And I felt that that might be a learning curve, a learning challenge for you, as opposed to not worrying about the 3D aspect of things and using something like a commercial game engine like Unity to help us with our assignment number 4. So on that, for assignment number 4, we're going to be using Unity, the Unity game engine, for that. So what that's going to do for you is it's going to free up some of your creativity. If you've used Unity before, this is going to be a boon. If you've never used Unity before, well, you got to learn how to use it, and in a matter of about a week. And I don't mean a lot. It doesn't have to be, a great deal of a great level of learning you have to do, but you need to understand it enough so that you can get it to work for your assignment. Now, here's the great thing about why we're doing Unity and the decision compared to you learning SDL, let's say an OpenGL version of SDL or another framework that you'd have to do with C++. Maybe in future iterations of this course, we'll make it with C++ and SDL and some kind of version of an OpenGL context. But for this semester, because we haven't really introduced you until now, and again, I think I probably would have done it with you guys 3 or 4 weeks ago, where I would have maybe the lab instructor kind of go over what it's like to do things in 3D a lot earlier, and that way you would have had time to play with it and learn about it and all that kind of stuff. So it would have made things a lot easier. So because we're not there, my thoughts are we're going to move towards a Unity, an option for Unity this last half of semester. All right, or last portion. So again, if you notice, it says week 12 is 3D collisions, week 13 is 3D collision response, and it says Unity all the way down. That's what we're going to do. I'm going to present assignment 4 to you, which should be available to you if you're part of a group. On that, I have to talk about groups. You have a chance to reform your groups for this last assignment if you didn't like the person you're working with before, or they didn't do a great job, or you felt that you'd like to try and go with someone else. We can certainly do that. I can arrange for you guys to disband your groups and come back into your groups afterwards, or set up groups with somebody else. Right now, the assignment groups are the ones that I'm using, but my thoughts are I may make a whole new set of assignment groups where you'd have to join, and I might do that at the end of today. So I'll say, for assignment groups for assignment 4 kind of thing, where we leave the other groups alone, but the ones for assignment 4 are going to be different. Okay? I'm just putting it out there to you because I know I've had a lot of feedback about, different team members' performance and people not doing what they're supposed to do and so on. And I want to give you guys all a chance to form up with other people. For this assignment, I'm going to give you the chance to work with up to 3 people. All right? So because it's a little bit more hefty in terms of what I'm asking you to do. And also there's assets to get. There's, you're learning Unity at the same time and a bunch of stuff. However, I do feel it's really important that you learn everything you need to, because we're going to be using Unity for the final exam, all right, coming up. So if you don't learn Unity now, you have 3 weeks to or a couple weeks anyway, to get familiar with it so that we're ready to go with the final exam. Again, I'm not going to make a very complex requirement for the final exam. You'll have the whole week to do it, just like before. But this time you'll be using Unity, so you'll have a lot more leeway in terms of what you can do. And we'll talk about Unity a little bit today. So, without further ado, let's get into the assignment details, which is now posted up online. So, assignment 4, 3D collision detection and response. This is due week 14 right now, Friday, December the 11th, 2020 at midnight. Sounds like it's far away because we just said December and we're in November, but actually it's 2 short weeks away. It's around the corner. And again, we're less than a month out from our holiday season, right? So, you know, we're kind of really nearing the end of semester here. The value for this one is 15% like assignment 3. And how is it working? Well, so this assignment is broken down into several parts. The physics simulation will be hosted in a separate scene. The best way to complete this assignment is to complete as much work as possible on your own and then get together with your group members. Programming required. This is a programming assignment. You'll be required to use the Unity game engine. I will not accept, in this case, STL, C++, or any other kind of programming language. You have to use C# and Unity, which means there's going to be a bit of a learning curve for some of you. And for some of you, you'll love it because you might already know Unity, or you know C#, or. Again, completing this assignment will help you with the final test. The final test is going to be with Unity because we're going to be using 3D. So, project assets. You will be responsible to acquire or create 3D meshes, textures, materials, and sound assets for the project. That's all up to you. Project constraints. Let's talk about this. You are not permitted to use the following. No Unity physics engine. Any physics plugin, no scripting plugins with third-party sources, no rigid body components, 2D and or 3D, no collider components, 3D and or 2D, no ray casting or line casting, or any other component, script, or system that provides physics simulations, collision detection, or collision responses. Is that clear? So even though you're using Unity, you're going to do collision detection on your own, which is what you would have done if I gave you C++ and STL anyway. So you're still going to code stuff. So for those people are thinking that, well, Unity is kind of a low-code, no-code kind of system. Yes, it can be, but not for you. For you, it's going to be just a vehicle for you to use a 3D context, and then you're going to still use everything you know how to do with the stuff that we've learned in class to apply it to Unity. Okay? Just as an aside, Unity was used in previous courses for the second course in the series of physics courses that we would do. We would do C++ and STL for the first course, for this course, and then the second physics course, you'd use Unity, right? So it's not a negative thing. I think it's a good thing, but it's around learning how to use the tool, which is going to be the thing, the sticking point for some of you, because maybe some of you haven't had a chance to do it. Yes. So I have to talk about. I know. It's. I got to talk about the constraints because it's like I feel like I'm. It's a disclaimer. You know, this may cause side effects, headaches, and vomiting. I don't know. One of those kind of things. You take a pill, it might make you feel good, but might also kill you. Right. So it's this kind of thing. All right. Let's go into the next part. The base project setup. You will use C# and the Unity game engine to create 2 scenes. Your application should include a start scene with labels. This is kind of similar to what we did before, and a button to get you to the main scene. The main scene will contain the physics simulation, and you should include appropriate assets for the physics simulation as indicated in part 1, which is down below. You should include appropriate 3D assets and have a texture applied. Appropriate lighting should also be including. So you have to talk about lighting and cameras and everything else. Let the user activate the play scene with a button or other control. That's like normal. Use appropriate label objects in your scene to show key statistics, which may include mass, position, velocity, acceleration, force, whatever you want in there. Allow the user to change the variables for each scene. Example, mass, velocity, friction, etc. Update your display accordingly when you change the variables. Do you have to do this in real time? No. You can also use the Unity editor to do this, as opposed to doing this in real time. So I would accept that. Provide the user with a button or other control within the main scene to go back to the start scene, because you want to be able to kind of start again if you want to, or maybe reset the whole scene. Part 1, the simple 3D collision detection and response. Using the Unity game engine, create a simple scene that includes a first-person player controller, a cannon prop, that fires bouncing balls and a series of at a series of blocks, it's at a series of blocks or 3D cubes. The player should be able to spawn bouncing balls that fire at the blocks to knock them down. Use the appropriate 3D collision detection and response techniques to solve this problem. So again, what you're doing is basically making a 3D block shooter, right? Kind of thing, right? So you're hitting it. The blocks with these bouncing balls, they're going to be spawned. I didn't say instantiated, notice, right? Because my expectation from you is to use object pooling. Oh yeah, buddies and peoples. Love you all, but you need to do some other techniques other than just using Unity. All right, so for this simulation, there's no scene boundary, but instead you're going to create a sandbox where the balls can bounce around, right? This could be an enclosed area or a room. Set up the scene's main camera at one end, so that's your player controller. And that's what this should read. Set up the scene's player controller with the main camera attached at one end of the sandbox so that the entire sandbox is clearly visible. Choose appropriate interesting assets to place in your sandbox. So you might choose, I don't know, some kind of obstacles or something else to put in there. I recommend keep it low. It doesn't have to be, you don't have to create other obstacles other than the blocks that I recommended. All right. The bouncing balls will be quote unquote fired from the player's cannon. There is no cannon, of course, it's just a prop. And they will collide with the sandbox's walls and other objects. They will maintain most of their momentum, however, some of their energy will be lost, similar to what you did in the 2D scene, and they will continue to slow down. Select an appropriate mass for the bouncing balls. When any ball comes completely to rest, right, it will despawn, and use of an object pool for your bullets, quote unquote, or bouncing balls is required. All right, so that's something that I'm going to be looking for. The player can move the player controller anywhere within the main scene sandbox using mouse and keyboard controls or a gamepad. And the player's controller should include a simple collider that prevents it from passing through walls of the scene or other objects. The player's controller does not have to include a mass property. So it doesn't have to be like, you're not going to bounce off walls. Your player controller is just there to fire bullets. I don't expect there to be any recoil or anything like that. It's just pretty simple. Yeah, more object pools, that's right, but in Unity. And finally, set up a series of 3D blocks or cubes. You can make these any shapes you want, something that makes sense for your scene. And at one end of the sandbox, when any ball hits the 3D blocks, they should fall to your sandbox's floor. Again, I don't expect any kind of rotation. I don't expect any kind of angular momentum, none of that. Make it possible for the user to adjust the block's mass and friction. Okay, this is new. For example, if the blocks have 0 friction, they will slide apart easily. But if they have a higher friction value, they demonstrate higher cohesion when being hit by a ball. If the blocks have a higher mass, several balls will have to hit the blocks to knock them over. All right, so pretty simple stuff. All right, so that's the problem that you have to solve. There's 4 little parts and this big part. It should give you a fair idea of what I'm asking for in the scene. I will definitely take questions after this, so you can ask your questions around what this thing is about. 2, a video demonstration like normal. 3, version control like normal. There are some tricks for version control for Unity. I'll have to talk about them today. And then finally, your project criteria remains the same with, again, what it says here is 15% of your total grade. And this is the breakdown, which is almost identical, if not identical, to the mark breakdown for assignment 3. Okay, so that is your assignment 4. It's out, it's due 2 weeks from now, and it's going to be done in Unity. Any questions? This is the time to ask, my friends. Please raise your hand if you have a question so I can take your question. Chris, come on the mic, Chris, and talk to me about what your question is. Yes.
So I was wondering if you had any kind of quick learning resources for Unity.
Oh yeah. We're actually gonna do some today with you. How about that?
Oh, okay. Cool.
Yeah. So we'll talk about that, and I'll also record everything, and you'll know what to do.
Okay. All right. Sounds good.
But yeah, there's definitely gonna be some. Okay, Yaniv, talk to me. Come on the mic, Yaniv.
So is this gonna affect the latter half of the course, like so that we're gonna be looking at the now?
Everything is going to be in Unity for the rest of the course. Yes.
Including the practical at the end?
The practical exam at the end is going to be in Unity. Yep.
Okay, gotcha.
All right. That's why I'm getting guys to use it, so that way you learn it, and then you're going to be good to go. Yeah, I know everyone's got to install stuff as well. So that's something that we're going to do. Good thing about the practical, again, you'll have the whole week to do it, so there's no pressure if something goes wrong. Sometimes what happens is when we use an application like Unity, it crashes. And this way, if you have the entire week to do it, you'll have the entire exam week to do your practical. It won't be as bad. That's the idea behind it. All right. Anyone else have any other questions? Tam, talk to me.
Yeah, can you explain more about collision and friction?
Can you come up a little bit higher? It's hard to hear you, man.
Oh.
Yeah, you're pretty low.
It's just Zoom.
Okay, sorry, I couldn't hear you. That's why. You're asking about, can I explain more about what? Friction. Okay. Yeah. Okay. So imagine you have. So this is back down here. So imagine if you have two blocks. They're on top of each other, right? If they have zero friction, and you hit them, doesn't matter how much mass they have. They're gone. They're going to slide off, right? But if they have mass and friction, then what's going to happen is there's going to be this resistance to movement, or kind of a coefficient of static friction that's going to prevent the blocks from moving apart, right? And that's what I want you guys to simulate, right? So when the blocks get hit, if they have a high coefficient of static friction, again, you can create that as in code. Then what's going to happen is they're going to slide apart less. They're going to be acting on each other based on their mass. So one block on top of another block, right? Which is going to make it so that you can't just literally fire something out, or the blocks won't move as much. Now they'll still have a chance to fly if they're lightweight. So mass makes a difference. So if the mass of the block is heavy, as an example, it's still going to take quite a few, let's say, bounces from the ball, or a series of balls, basically to knock the blocks over. I would say so, yeah. If you're going to normalize it, Tam, and Tam's question is, if it gets stuck to the blocks if the friction is coefficient is 1 and it slides right off at 0, I would say, yeah, if you're going to normalize it between 0 and 1, I think that's exactly what would happen. All right. So I want it to look something like this. Okay, let me see what I can see. Yeah, kind of. You have this thing that's firing. You're kind of basically, yeah, like a shooting a Jenga tower. Exactly. Again, it's kind of very straightforward. I like your little drawing. We'll talk about it more as we go forward. All right. Any other questions? If you want to put up your hand before we move on, because I want to talk about the main meat and potatoes of this of today. Right. So lots of really good fun. So I encourage you while we're talking, because I'm going to be asking you to download Unity. Let's look online for resources. So up online, I've got my kind of my live thing on YouTube right now. So for people who need closed captioning support, it's there. I've got a link to download Unity. So download Unity Hub is what you're going to do. There is Unity Learn resources. So if you go there for Unity Learn, you're going to see that there is a skill level. You see, I was just trying it out, but you can see that if you wanted to look at how to learn Unity, you can do it right here. I'm going to show you I'm going to show you Unity today. But I encourage you, if you've never used Unity, to do it. There's a lot of little levels and things that you can kind of show to do what you need to do. They have different experience points, if you will. That's how they do it, an XP system. Actually, similar to what Wallace does in his courses, where he gets you to do extra stuff. Where everything from design to art to scripting, game development, which is where you want to go, and you can learn a lot from just the Unity site for free. Then there is the other thing is physics hypertext book, which is actually one of my followers on YouTube recommended this. He put it up on as a comment in one of our videos. And it's not a bad idea. It basically steps you through all the different things you need. I think it's a good resource for what we're doing in terms of dynamic forces, energy, rotation mechanics, motions, and a bunch of other stuff. This is pretty cool to look at. An example of this would be if we did any of the mechanics that we've been doing in the first half. So for example, free fall or kinematics, projectiles. Here's one that might look pretty good. It talks about projectiles at length, and it's like a little physics textbook that's online, and it gives you all the formula love that you might want. Okay, there it is for you. Okay, so that's pretty cool. So take a look at that if that's going to help you. All right, so that is some resources. But we're going to load Unity right now. And I want to, while I'm lecturing, what I'd like you to do is download Unity Hub. So that's the first thing I want you to do, right? And with Unity Hub, what I want you to do here is, and I've got, several projects, but I want you to go to installs. And when you install, I'm using Unity 2020.1.10F1. I recommend that you also use the same. All right. So what I'm asking you to do is please, no Unity Bolt. What I'm asking you to do here is please try and adhere to the same version as me, so that way when I launch your Unity or if I share something with you over the next couple weeks, it's going to be the same version. Okay, but how do you do that? Because I'm at 10F1, and if I click add, then it's going to show the latest version is 2021-15F1. Okay, there's some bug fixes here, but really I'm working within the same version as you. 2020.1 is the official release. 15.F1, there's like few minor patches that have been done, but nothing different. I'm recommending to you that I want you to download 10F1, but where is it? Well, you can go to where it says download archive. So this download archive here, if you go to the download archive, you can see that there is every Unity version that's been released over several years. Everything from Unity 3.x and up is available here. What I want you to do is grab this one. Okay, this is Unity 2020.1.10. That's the one I want you to grab. It's from October of this year, so it's not old necessarily, but this way we'll stay in connection with one another in terms of our version. Okay, so if I download your stuff, you download my stuff, we're at the same point. By the way, it wouldn't matter if I told you to download 1.15, because next week they're going to come up with another one. Look at the dates, like 19th of November, 11th of November, 5th of November. Every week, pretty much, they have a weekly build that they come up with every single week for the entire year, pretty much, right? So it doesn't really matter if we were to go with something newer. If you try to get the latest bleeding edge release every single time, we'd be out of sync. So let's just go and use 2020.1.10, and I'm going to get this archive link for you just to make it easy, and I'll put a link for this inside of our Blackboard. All right, so I'm going to go here, and I'll say the Unity download archive is here, just in case you need to go there and you don't know where to get that, or you missed that in the Unity Hub area. This is the one that you want. Okay, so let's bring this up to this point right here. All right, so that is what I'm asking you to do. So it's going to be version of Unity 1.10F1. Notice that I have different installs. One thing is when you install Unity, it's going to ask you what components you want Unity to use, and we have to talk about these platforms as components. So if I was going to download and install, let's say 2020.1.15F1, then it's going to ask me, well, which platforms do you want, right? I don't care about Microsoft Visual Studio Community 2019, so please don't check that. I don't really care about you building an Android support. I'm using that for our class in third year, so you don't need that. Or iOS support, you don't need that. You're not building a Mac or Android or iOS or Android app. You don't need Mac build support unless you're using a Mac. But if you're using a Mac, please also include Universal Windows Platform and Windows build support. Those three, okay? Also, what I'm going to get you to do this semester is also do WebGL support. So I'm going to probably get you to do something on the web. So please try these last four. Really, you really don't need Universal Windows Platform. So if I was going to cut this down so you can save 2.2 gigabytes, just if you're going to use a Mac, then it's Mac, WebGL, and Windows. If you don't have a Mac, then it's just WebGL and Windows, these last two. So really, that'll save you a pile of storage space. For Unity, it can be up to I mean, depending on if you load everything, it could be 10 gigs or more, right? Uncompressed. So that I recommend don't do that. Also, don't download the documentation. You don't need that. You can get a lot of this stuff online, and I almost never use this. I never check this out. So that's all you would need in terms of your installation requirements. All right. So again, 2020 10F1 is what I want, and I'm gonna wait. We're gonna come back to this. I'm going to leave Unity Hub up because the last part of our little example today is a little demo with Unity to give you a little bit of a tour about how everything works. Okay? If you're not confident about doing that. So for now, please, while I'm talking about this stuff with you, yes, Vincent, WebGL on Windows. While I'm talking with you, please download and install the latest version of Unity Hub if you don't have it already, as well as this version 2020.1 10F1 with at least WebGL and Windows support. Okay, let's get into our lecture part. And before we get there, any other questions related to Unity or any concerns? I'm sorry, Yanniv is sharing another picture with me. Okay, 2.42 is available. Right. Okay, thank you for that. All right, so any other questions around that? It's absolutely recorded, Anna. It's being actually broadcast right now on YouTube. Okay, so let's continue. So we're talking about 3D collision detection, and even though there's 57 slides, it's going to go quick, and I want it to go quick because I want to get into Unity a little bit with you guys. All right, so let's get into that. So really, when we think about collision detection for games in general, we think about basic building blocks, fundamental geometric shapes like line segments, planes, and boxes and spheres, those kind of things. Without those things, we really can't create a bounding volume, and we've been talking about this over the last several weeks, and even before that, when you did your game fundamentals in first semester, right? We've been talking about bounding volumes. How do I make a bounding volumes or a bounding box? And then through the bounding box, I'm going to collide with or intersect, overlap with another bounding volume. It's going to be the same in 3D, okay? With some provisos. There's certain things that are going to work better than others when you start doing things with 3D and no colliders, okay? Remember, Unity's colliders, they're very smart the way they've worked. And you really can't create a system like that in the 3 weeks that you have. So let's continue with what we have. So we talked about line segments. Here, instead of a vector 2D, we have a vector 3D. We can use a 3D line segment. So you can port over a lot of the code that I've given you already in 2D. You can bring it over into 3D. You can convert it into 3D, which is what you would have to do anyway, right? If you're going to do a line test or something like that. The same tests that work in 2D, you can extend to 3D. Okay, all you're doing is adding an extra component, the Z component, okay? One thing to note about Unity is, and we're going to talk about this, is how do you, what is the coordinate space orientation? Some programs, for example, like Blender, let's go back into Blender, and you may need to use Blender for asset creation. Even simple asset creation you can do in Blender. One day when Blender decides to open for me, here he is, you can see that I have a Z up as a 3D orientation default. So I have my cube here, and you got your y-axis here and your x-axis here. This is not the case in Unity. In Unity, we have a y up, right? So we have the xz plane as opposed to the xy plane. So keep that in mind. Depending on the orientation, you may have to make your calculations slightly different. All right, but for the most part, that is the line kind of a line test or line segment. These are basic building blocks, again, we're talking about. The other one is, sometimes what I want to do is I want to find the point on a segment. And the way to do that, of course, is you get your line start. And what you want to do is you want to calculate, right, a point T on the line. Now, if you think about what this is, this formula is really the formula for LIRP, linear interpolation. You're interpolating the distance between one point and another. That's what you're doing with a line segment anyway. So you can calculate the point on a line. This is a key building block when it comes to detecting where the line is. Now, one thing I said was you cannot use ray casting in Unity, but you can make your own rays if you want. If you've got the wherewithal or the programming chops to make your own rays, right? Line plane detection, which is really what rays are in some ways, or line point detection, then that could go a long way into providing a lot of different things for you. Things like ground checks. Am I grounded? Things like distance checks from one thing to the other. A lot of the things that you can do in terms of where an object collides. Again, you can use some of these same formulae to do that. All right. The other thing we want to do sometimes is detect where on the line, and the way to do that is we can imagine different line segments. There's a few cases, okay, when we want to detect where on the line or where the object is in relation to the line that we're kind of calculating the collision. The case one is it's closer to the A point A. Might be outside of the line but closer to point A. It might be outside the line but closer to point B, or it might be between point A and point B. Those are the three options, the three cases to consider when it comes to the minimal distance between a line segment and an arbitrary point. Okay, so it really depends on where that is. And the reason why we want to know this is because it can help us with collision detection. Okay, I'm just going to continue on here. And nicely, you've been given a little line segment minimum distance squared test between a vector 3 and a point. Now, one thing we're going to know about Unity is that we're going to be given a couple of things. One, the line, right? As an example, notice that line segment itself has something called, in this case, has something called minimum squared distance. So minimum squared distance is actually a method that belongs to line segment. Right here, you can do that in different ways, but you can use similar calculations to figure out where on the line segment you're colliding with. Guys, this is key to any kind of ray casting because you want to get kind of a ray cast hit. Where did if I'm casting a ray, a line from one point to another in three-dimensional space, I want to know how far on that line did I hit? Where is that? And if I hit multiple objects, what object did I collide with first? So I know if I, as an example, have things like line of sight. Okay. So it's like a normal or an attack vector. Yes, there's a lot of different things you can call this. Let's continue. Planes. Planes are another, we've talked about this before, but now we're not talking about just line segments anymore. We're in 3D. Even though it's a flat two-dimensional surface and it says that extends infinitely or can extend infinitely, we can use this as another way of bounding our area. Now you're making something in 3D. I've asked you to make a sandbox. You can design a sandbox in any way you like. You can piece it together with tiles. So for example, and what I mean by that is make it with a bunch of quads. You can make a sandbox with one big plane and then a bunch of planes that make a box around it and a roof. Because remember, you're going to be firing these bouncing balls at these blocks, right? From your main character controller. So when you fire, from, let's say, this cannon prop, it's going to appear inside of your main character controller. This is the kind of stuff that you're going to be doing. I think it's important to understand how you bound your area. All right, so that is the equation of a plane. That's what we're looking at. So that is that. We're going to continue. So if we have a plane here in Unity, if I was going to make a struct, again, structs are available in C#, just like they are in C++. As an example, vector 3, we have a normal direction, and then we have some kind of float, which is the distance. So what we want to do is we want to extend that normal across the entire distance. That's one way that they do it. Okay, but really what we want to know is a plane, if you think about it, is a rectangular surface that has some kind of normal direction. All right. And here what we can do is when we want to think about a plane, as an example, there's many ways to construct it. You've been learning about OpenGL. And remember, whenever we make a plane or a quad, that quad is subdivided, or a mesh, that mesh is subdivided into at least two triangles. All right? So when we do mesh construction in Unity, which happens automatically, there's always at least 2 triangles that have been created for every quad, right? Now, for us, we don't really care. All we care about is the bounding volume. We care about the start position and the end position, as an example of, or the top left corner and bottom right corner of the plane, wherever that is, and the normal. That's what we care about more than anything else. You get a lot of that information from Unity. All right, let's talk about bounding volumes in a little bit more detail. There are different kinds of volumes you can use. The 2 most common bounding volumes are boxes and spheres. So let's think about this. If I have a sphere, all it is a center, some kind of vector 3 in the center, with a radius. And that provides us the sphere bounding area. I don't have to draw the sphere, right? I mean, you could, but there's no need for it. And in fact, if anything, it'll actually increase your performance degradation, right? It'll increase the number of calculations if you want to calculate a sphere while you're moving around. You don't need to do that. All you need to know is what's the center of the sphere and what's the radius from the center. Anything that's inside of that, or the radius, then you have a collision. And this is one of the most common bounding areas. Why? Because I can surround a sphere around anything, really. Right? Whether it's a ball. Now, I mean, obviously a ball would be perfect, right? Because it's spherical, right? But any other surface is okay as well, even a box. However, we talked about this last week and maybe the week before. It's not a great logical, it makes a good logical collision, easy, but from a visual collision, that would be a problem. So, no, I would say this is not a great option, right? So if I was going to annotate this just for a second, I would say, you know what, this is probably not good. This is probably not really that good. This is, this is okay. This can probably work if you make the sphere smaller. And this is okay because these are kind of things that can work, all right, if you make the sphere smaller. Here doesn't make any sense, right? Because look, you have all this area here, right? And you have these areas in here that, from a sphere perspective, doesn't make any sense. However, I have to talk about this in terms of, again, we're going to go to realism versus playability here again, right? And sometimes what we want to do is we want to say, well, this might not be right, but if you make the sphere small enough, it might almost be good enough, right? When it comes to long-range collision detection. However, obviously a box collider would be best here. And it's the least expensive as well. All right, so just wanted to talk about that a little bit because of that is something that you're going to run into. All right, so one thing that we use a lot is axis-aligned bounding boxes. Now, this is the true box, not just a rectangular object. It's a rectangular prism that kind of bounds an object. And we can see that it's still an AABB type collision detection, but in this case, we have our min and our max. Again, top left corner, bottom right corner of our bounding volume. And again, now we have a much larger volume than what we've had before. We have 6 planes, right, to make up the box, if you think about it. But really, we want to talk about things in terms of a range. I have the top left range and the bottom right range. Anything inside of that range of pixels or points, I have a collision. All right, that's really what it is. Okay, minimum and maximum. So, and here we can do this. Sometimes what we have to do when we move an object around, we want to update the minimum and the maximum points. So as an update is moving, or as the box is moving, we want to update it. So we want to update the AABB, right? And we want to do it for each component, for the X, Y, and Z components of the min and the maximum plane, maximum points. Okay, and once we have that information, once we have this update method, then I can simply do AABB type collision detection with a box as opposed to with something else. And you can see that a box might be okay for a character. And if I go back up a step for a second, back to where we had that sphere, this may be not so good. But again, let's say if we annotate as an example, and if we try and draw, I don't have any drawing tools to do that right here. Maybe I do. I do. Ha ha ha. So let's suppose I want to draw a box volume. That's a little tighter, right, than the sphere. Sphere wouldn't make any sense. Again, box volume for this kind of stuff makes perfect sense. And even for the little spaceship, box volume can be okay too, depending on how you do it. Again, there's some visual distortion here, here, and here. Again, I might think about the sphere being good, but the ball would not be good. This would not be good. The ball would not bounce properly. You'd have some points on the end that would not be good. So in terms of what I would like, I would say that, this is kind of okay for a box. This is probably okay. Maybe this one, as an example, but you know what? This one, no, right? I don't think that those are good at all, right? So let's go from there. Capsule collider for sure. We'll talk about the capsule collider in a second. All right, so let's talk about these things. Oops. Let's clear that one and stop the annotations for a second and move on. Oh, I gotta clear the annotations. Clear all drawings. All right, let's go to what we were talking about here. So you can see that I can bound a volume even if it's misaligned. This is okay, but this, I have to say this is no good. All right, I mean because of this part in here, right? This part in here, it's not good for it to be like this. If it was some kind of bounding volume and you have an object that goes on like this would be bad. And this is where we speak about an object-aligned bounding box instead. So a different kind of collision detection technique than what we've practiced so far. Okay. All right. So again, one way to complete the AABB is, again, after rotation, is to first construct the 8 points representing the corners of the AABB. And then these points are simply all possible permutations of the min, max, x, y, and z components. That's pretty cool. We update the min, max like we saw earlier, and then when they're rotated, which is kind of a good example of what to do. And here is an example of some pseudocode that can help us do just that, right? So we have to rotate. We're rotating an AABB. So if I was going to make an AABB type collision class, you can definitely use this pseudocode to update each of the objects based on its rotation. Notice that it takes in a quaternion, and you can use this with GLM and OpenGL, but you can also easily do this with Unity because quaternions exist as a data type in Unity that we can use, and that's why I'm really happy about using that right now. But you can see that there are 8 points from 0 to 7, and you can calculate each of the points of the permutations between all the points. And once we've calculated the permutations in terms of rotation for this particular AABB, I update it, and of course what I return back out again, or I actually update this AABBs, like I actually update the points. But if I wanted to make it so that it's static, I could just return an array of points, the new rotation matrix, if you will. Okay. You can also use matrices if you like as well, which is also something that's very commonly used instead of using, just these points. But notice what we do is we can do a transform, right? That we can perform on an AABB in order for us to not just rotate but also translate. Okay. This is better. Remember that check mark? We had an X for this kind of thing before when we were using an AABB. Again, if I was going to use an AABB type collision detection, maybe that's not going to be the best kind of shape. The collision shape would be bad if I did this. Take a look at all that wasted space here if I did this. But with an OBB, or an oriented bounding box, or object-aligned bounding box, if you will, we have a vector 3, which is the center, so something in here, all right, some kind of center point, and then a quaternion rotation, all right, so some kind of rotation point, right, and then a vector 3 for the extents, which is kind of neat. Again, you can do this all within Unity nicely. You don't have to worry about data types like quaternion or figure out how that works. But basically what you want to do is you want to figure out the extents. So the extents would be kind of the maximums. You want to find basically these points. Those are the extents. All right? Okay, so once you find out those points, then you have information. You have enough information to create your bounding area. Now, there's other ways to do an object-oriented bounding box. And the way to do that, of course, would be to surround the box with a series of planes, right? Or a series of lines, right? So you can make a bunch of lines, how many edges are in a rectangular prism? Who knows that? Who can remember how many edges? First of all, how many? Remember, whenever we talk about three-dimensional shapes, there are 3 parameters to every three-dimensional shape, right? 3 parameters. Let me just stop this and de-annotate here for a second and go back to Blender, right? The first parameter is if I go into, if I tab into edit mode here as an example, you can see that the first parameter is the point, the vertex, right? We have vertices, right? And the other thing is we have edges. So we have an edge, right, which is just a line. That's all that is, from one point to the other. And as an example, and how many edges do we have in a box? So we have 1, 2, 3, 4 on the bottom, right? So say if we want to look at, kind of a wireframe. Here's the wireframe of our box. There's 1, 2, 3, 4 on the bottom, 1, 2, 3, 4 on the top, right? And 1, 2, 3, 4. So 4 times 4, 3 times 4 is 12. We have 12 edges, right? So 12 lines. So worst case scenario, if you wanted to construct, your bounding volume on your own, you could literally just use lines. That's why a line is such a primitive, or building block, a fundamental building block of creating any kind of, bounding area is what you're looking at, okay? So again, you have vertices, right? Sorry, you have vertices, you have edges, and you have faces. So here's this is a face, right? So you have faces, right? And I can, in Blender or in Unity or something else, I can subdivide this into smaller areas, right? Where you can see this smaller area. I can further subdivide this as much as I want, but at the end of the day, every one of these things that we see here is really a bunch of quads. That's what's been happening here to make this thing up. We have a bunch of quads, and every time we subdivide it and create additional geometry, whether it's in 3D with Blender or Unity or OpenGL, what you really have is a bunch of triangles. So here in Blender, you can see the number of triangles if you really want to, and you can do that in Unity too, right? I can go to my add modifier and I can triangulate, right? Here I can triangulate. I can also keep the normals if I want, right? And once I triangulate, it actually creates all the triangles here that I'd like. All right, so that's one thing you can do. You can actually show all the triangles, right? So if I go back to wireframes now, you can see that I have a bunch of triangles, right? Or that break up each of the quads, right? So that's what's kind of happening. So we're going to see that you can use a lot of, you can create a lot of information here. But one thing to note is this: it's literally, if anything, all shapes are really a collection of vertices, edges, and faces, where all we care about, we don't even care about face collision necessarily so much that we care about edges and verts, okay, more than anything else, okay? So just, putting it out there for you guys. All right, going back to this then, we have some information of an oriented bounding box and how that would work for us. Capsules, someone mentioned capsules. Capsules are actually really easy to do, right? All we need is a line segment and a radius. It's like we have a sphere, similar to what we call the swept sphere, from one part to the other. So notice if I go back to Blender, and let's just drop out of there and let's delete the cube, and I want to add a new volume. I have these options, right? Do you see in here that I have an option for a capsule at all? No, a lot of drawing programs don't have that, but I do have options for spheres, and I do have options for cylinders. So really, I can take a cylinder, right? So here's my cylinder. I could chop my cylinder up, right? So I can kind of go to the top, control, take the top face off the cylinder. So let's get rid of the face of the top. Let's get rid of the face for the bottom. So you got your cylinder here. And then what I can do is I can add a sphere, right? So I can add 2 spheres. So let's go back to Shift A. Let's add in a sphere. Again, there's different kinds of sphere in Blender. a UV sphere and an icosphere. We care about a UV sphere for now, so there's our UV sphere. And what I want to do is I want to move it across the z-axis, let's say 1 point approximately. There's the top of our capsule, right? And I can do another one. So I can shift A and add another sphere, right? UV sphere. And I can, again, move it across the z-axis, let's say -1. And then now we have our capsule. Oops, undo. Undo. Sorry. Move it across the z-axis -1. And now we have our capsule. So if I undo, it looks like we have a capsule. So that's really what a capsule is. A hemisphere on the top, a hemisphere on the bottom, and a cylinder in the middle, right? And we can do that, in very simple terms. So we have a sphere on the top and a sphere on the bottom, right? And then we have a line that goes between the two spheres. Anything that's inside this radius, we have two things. A radius, which is the thing that goes from here into the middle, and then a line segment that goes from the middle of this sphere to the middle of this sphere. That's really what we're talking about when it comes to, to having a capsule. Now, great thing is that Unity comes with a capsule mesh. You don't have to make one yourself here in Blender and import it to Unity. But I'm just talking about how we would construct it when it comes to math. If I was going to construct a capsule, what would I do? Two spheres and a line, right? And really, that's what it is. And if you notice, if I go back to our example, that's exactly what we have. We have a radius, which represents the sphere. So the radius that goes up from here, right? And then a line that goes from here to here. So we calculate the radius from this part, from this endpoint out, and from this endpoint out, and we have a line segment between, right? And the line segment, the width of this is literally just the radius of the sphere. So the width here, everywhere else below the sphere area. So this is a really good thing. And when it comes to characters in 3D, I would say that the capsule collider in general, as well as for everything else, I would say is kind of like the best thing for a character that they can use. Why? This part here. This part here makes it so that when a character is on the ground, so this is the ground, I can detect when the character is grounded, right? And a lot of times we use either some kind of capsule collider to use that, or we use ray casting from the center of the character's point. We kind of consider the character almost like a mass, and the center of mass we cast downwards. And if we cast downwards to the plane, we can say that, hey, do I collide straight down with the plane? If I'm colliding with the plane, then I am grounded, right? And you don't make this line length infinite. You just make it slightly below the character's feet. So a couple ways to do that, right? So one, do I detect a physical collision with the sphere, right? Do I do that? And the second thing is, especially when it comes to slopes too. From a slope perspective, you can see that the sphere will be superior to a box, right? If you use a box, that would work too, but the box would do this, right? So you'd have this problem. And so this problem, it wouldn't work nicely for a slope, but for a sphere, yeah, that's okay, right? Sphere can work. Sphere can work here, sphere can work here. And that's why we use a capsule in general for a character a lot of times. Okay, so that is really a very simple construct that we can use. I don't think it's very challenging at all. And again, you may want to consider this if you're going to make some kind of complex character. What about convex polygons? So convex polygons are also a good way of doing things. Remember what convex is? Convex versus concave. If I was going to draw it for you, again, let's use the annotator for now. So let's suppose I have a basic shape. Let's see if I can grab a basic shape here, like maybe something that looks like this. Here's a basic shape. And, as an example, this would be a convex shape, right? Because, if I was going to bound it, if I used another kind of bounding volume, this would be bad, but let's suppose I use something like a box collider here, then you can see that I would kind of bound the shape. But I can also make it so that, let me just clear that drawing. Let's suppose that I have an odd shaped object, and we've talked about this before as well. So my the shape of my object might be something that looks like, well, I have a point that goes here, maybe here, 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 and maybe it's rough. Maybe it goes kind of like this. That's okay. That's still a convex area, except for this part, right? This part here would be concave, right? So for convex polygons, then it's easy for me to draw a series of vertices in a clockwise ordering direction, where I'm basically going from this to this to this to this to this, like this. Imagine if I had something that looked like this, not this part in here. So I don't have, let's say I don't have this part. Oops, erase the whole thing. But let's suppose I don't have that part, right? Then that's okay. And why is this good? What does this produce for us? Well, it produces for us a different kind of area for us, right? So the great thing is, and this is a really awesome thing, this convex polygon is a polygon collider. A polygon collider. I know, eh? I totally messed that one up. And that's really cool, right? So a polygon collider is like a mesh collider, if you think about it, right? We can use a polygon collider for 2D, right? Or we can use a polygon collider for 3D. So again, if I had a bounding volume, let's go back to what we had before, I can make the polygon, as long as it's convex, then I can just connect all the area, kind of the points together from one point to the other. And once I have that point, I can kind of, contain or bound. I create a bounding volume, right? As an example, especially if it's something like 3D, where I don't care, I can kind of create a bounding volume in 3D that is more complex, as an example, to bound an area than maybe that I can handle by myself, something like some weird kind of shape like in 3D, right? And why is this good? It's good because it gives me more flexibility than if I was just calculating something like a sphere or a cube. But I have to warn you that using convex polygons to create collider shapes is more computationally expensive than either a sphere or a cube, or even an object-oriented bounding volume. Why? Because I have a vector, so an array, if you will, of vector 2's, right? Or an array of vector 3's, which is more like it. Okay? All right. So when we do intersection tests, this is what we want to do when it comes to 3D, right? We want, one of the major tests that we do a lot is contains point. So I have an object or a bounding volume, and I want to know that that object contains a point. Okay, that's, again, these are fundamentals that we're talking about here, right? So we might have a sphere. The sphere might have a contains method. Does the sphere contain a vector? Why would I want this? Well, this is pixel perfect kind of collision detection, or point perfect collision. Sometimes I want to know if a specific point is inside of a bounding volume, and if I do, I can get much closer and much more accurate collision detection. So how do I do this? I calculate the squared distance between the center of my circle, so circle center. I subtract the point, right? And I calculate the squared magnitude, that's what the squared length is, the squared magnitude between those 2 points. And that becomes my squared distance, okay? And what I return is, if the squared distance is less than or equal to the radius of my sphere, right, times the radius, the squared radius, which is great. I can calculate where, if a vector 3 lies inside of my sphere anywhere. Guys, this is a key fundamental building block of collision detection in 3D. If I know this, if I know a sphere contains, wow, I have so much information. I can do a lot of information with this. I can even know where it's going to be colliding. The other one that's really important is the AABB contains. So I remember I talked about different bounding volumes. AABB is the other type of bounding volume that I want to talk about. And here, as an example, is we have the same thing. I have an AABB with extents. So I have a min, max, right? Min and maximum values. And then here I have some vector 3 point. And what I'm doing is I'm comparing each of the components of the point with the components of the min and maximum values of the box. Once I know that, I can tell that the point is inside of the box, right? Again, really great when it comes to doing things like, remember, the point can be anything. The point can be the end of my line, as a good example, right? As soon as my line enters I can do a point or sphere or box contains test. Wow, I have so much information already, right, about what to do. So this is kind of collision detection we're talking about again in 3D. Okay, capsule contains. Again, remember our capsule is nothing but a radius and a line segment. That's really how we calculate a capsule. We don't have to draw the bounding volume. We just need to calculate the bounding volume. So here what we're going to say is, okay, so I'm going to take a vector 3 point. I'm going to calculate the squared distance between the line segment and the point. Remember that line segment point distance? We can do that. And once we have that, we can say if the squared distance is less than the radius squared, we have a collision. It's inside of the capsule volume. Again, really useful kind of information. And Yana is asking, is it like wrapping? I guess yes, it is. Convex polygon contains point. This is for 2D. It doesn't matter if it's 2D, you can extend it to 3D, but this is a great bounding volume to use with 2D collision detection. It's like a mesh that you're creating, right, with different triangles. I can create this triangle mesh idea, so I can surround an object with different bounding volume. Okay, and there's the polygon contains. I'm going to move on from that. And sphere versus sphere, again, guys, the most common, I would say, collision detection test. AABB versus AABB. This is also very common, right? I mean, two bounding boxes, whether it's 2D or 3D. You have this X, Y, and Z collision detection. Pretty simple. I would recommend you're probably going to use this 90% of the time when it comes to volumes. Remember, you can create a composite collider that includes more than one bounding box volume, or you can combine things like a bounding box and a bounding sphere, and to create more complex shapes. But that means you have to check each of the volumes yourself, right? As an example, for each game object. Okay, and then there's a sphere versus AABB test. Guys, you need to do this in your assignment number 4. You need to create and I already have a circle AABB test. I've already provided that for you in what I've given you for SDL Engine. That's inside your collision manager. You can almost literally lift that information and put it in here. But I'm going to provide that for you here, a sphere versus AABB test, because really what we're doing is we're going to use the math max and math min. Now in Unity, it's called math f. We want to use math f functions for a lot of the stuff. We're going to talk about that soon. But you can see here, if I want to find the minimum squared distance between an AABB and some kind of vector, right, we can use the math max and math min to figure this out. And once I have the minimum squared distance between a point, then what I can do is I can calculate if there is an intersect between a sphere and a bounding box. If I can calculate the squared distance, minimum distance, if you will, between the box and the center of the sphere, then I can compare the squared distance. If the squared distance is less than the squared radius of the sphere, then I have a collision between the two. It's actually quite easy to do in 3D. Capsule versus capsule. This is more complex to do because we have a much more complex bounding volume, but this is also possible, and there's the little pseudocode to do that. Line segment versus plane. Guys, this again would be a fundamental. If I have line segment in plane, I have ray casting. I have ray casting, right? Because if I cast a ray from my character and it hits an object in front of me, and because I haven't asked you for rotations, chances are it's going to be axis aligned. I can tell that my ray is hitting an object. I can give myself line of sight. I can do all kinds of beautiful things when it comes to, when I have a line segment in a plane. And now, of course, we've given you that little pseudocode as well. Line segment and plane test. Okay. Line, segment, and sphere also key. Plane, sphere, and you can do things. There's a few cases here for line, segment, and sphere because line, segments, and spheres are a little weird. You have a case number 1 where the line segment lies outside of the sphere. You have a case number 2 where the line segment is tangential to the sphere, all right, a tangent to the sphere. And you have a line segment that is cuts across the sphere, right, or a secant line, if you will, that cuts across the sphere itself or bisects the sphere, all right. So those are the 3 different kinds of cases where you have more than one contact point, or no contact points. And you've got those cases right here. We have a line, segment, sphere test. So we have an example right here of our pseudocode. All right, so pretty cool stuff. Line, segment, AABB test, also a key. Notice that it's very similar to the sphere. We have those three cases. No collision, no contact. One contact, where part of the line lies inside of the bounding volume, and the other one where a line bisects a rectangular prism and gives us two contact points at least. Okay. So line, segment versus AABB. So these are all the different tests that you can create to help you with collision detection for your assignment. Remember, for the assignment, you are not allowed to use any collider. You are not allowed to use any kind of physics that's built into Unity. You have to make everything on your own, all right? Which makes it so that it's more challenging for you and it's more realistic. All we're using Unity for, really, at the end of the day, it's not going to make it easier. It's just going to make it easier for you to draw everything. And the interface is going to give you more feedback. So it's going to be a lot easier and nicer to work with as opposed to something like SDL and C++. But it doesn't mean that it's going to solve anything for you. Okay, there's no solution coming out of Unity for this unless you use the physics built in. So again, line, segment, AABB test. It talks about how to do a test plane and an intersect test, as well as what about this, dynamic objects? And this is what I kind of alluded to, kind of last week. I said, what if you have a very fast-moving object, a very fast, small moving object that is, you're going to be checking every frame. You may have this a miss, right? So what you want to do is what we talked about before, which is this idea of a swept sphere intersection. And I've given you the pseudocode for this as well, where you have two spheres, and what you're doing is you're casting a sphere in front of the bullet or projectile, and you're going to try and find out if this thing will collide in the next frame. And that's really it. That's all that I wanted to talk about in terms of theory for today. Questions before we move on to the Unity stuff? All right, here's what I'm going to do. I'm going to stop recording this on YouTube and then go and re-record, start another recording, right, that's separate just for Unity for your course. So this way you can go right to the Unity stuff. You can do the theory part separately, and you can do the Unity part separately. So I'm going to stop recording now. Give me a second. I'll set it up. And for the remainder of the day, we will do a little bit of a Unity tour, right? And I'm hoping that you've already downloaded Unity already. Let's stop this. All right, guys.